Hello and good evening. My name is Ahmad Hazi, and today I'll be presenting my lab report of fluid dynamics about Bernoulli's theorem. For the introduction, according to the Bernoulli's principle, when the area available for the fluid to flow decreases, then flow velocity of the fluid increases, and at the meanwhile time, the fluid pressure or the fluid potential energy decreases. This principle is named after the Daniel Bernoulli, who first wrote this principle in a book named Hydrodynamic. Some applications for this particular theory are: first one is air flight, second is lift, the third one is baseball, and the fourth one is sailing. The main objective of this experiment is to compare the behavior of ideal fluid and real fluid with the aid of a venture-meter apparatus to study the effect of area of the flow velocity and fluid pressure using Bernoulli's equations to compare the behavior of the ideal and real fluid. Now let's get into the theory. According to Miller, law of conservation of energy was the main deriving factor behind the derivation of the Bernoulli's principle. Bernoulli's principle states that in a steady flowing fluid, the sum of all mechanical energies, including kinetic energy, dynamic head, fluid pressure, and potential energy, should remain the same at all the point of the flow. So if any type of energy increases, like if kinetic energy increases, then the other type of energy, like potential energy, pressure, will decrease to make the final sum the same as before. And according to Bernoulli equation, a flowing fluid have three things. The first one is pressure head, kinetic energy, and potential energy. And here we have the equation that we're going to use for this particular experiment. And in the above equation, P means the fluid pressure, the V is the flow velocity, Z is the height of the fluid, and P is the density. From Bernoulli's principle, it can be stated that the density and pressure are inversely proportional to each other. Means high density fluid will apply more pressure while moving than the low density fluids. In the horizontal pipe, where the inlet and outlet of the fluid are the same height, the Z quantity can be removed to give the above mentioned equation of Bernoulli principle a new look from where we can calculate the height at any point of the flow, if we have the initial height of the flow and the velocity at respective positions. And here's the few derivation of the equation, which can be used later on. Now let's get into the methodology. The first step is to place the venture-meter onto a horizontal surface and note the height of input valve and output valve and make sure they are the same. Attach the apparatus with the power supply but keep the supply off. Open all the air bleed valve of the manometer present at the top. On the power supply to run the pump and adjust the flow rate control valve until water level in all the manometers is at readable range. Next, place stop plug in the basin. Note the time required to fill the basin with specific amount of water. And remove the stop plug to drain out all the water from the basin. Place the dynamic pressure probe with the static pressure port and measure the manometer data from both of the probes. Now we have to place the dynamic pressure probe with the next static pressure probe and measure the manometer data from the probes. Repeat the above step for measuring data from all the manometer probes. Turn off the pumps and set off the power supply. And for the apparatus in this experiment, we are using a venture-meter, supply hoses, and a measuring tank. And here's the sample calculation using the formula given in the theory before, in the slides before. And here's the experiment data. Here's the first run. And this one is for the second run, and then the third run. And this is the graph for run 1 and 2 on the left side and the run 3 on the right side. Now let's get into the discussion. From the calculation, it is very clear that with the decrease in area of the flow velocity increases and the pressure decreases. As shown in the graph of all the three tests, the decrease in area of the flow decreases the height of water in manometer column, means they are directly proportional to each other. Difference in the theoretical and measured value, it can be said that the water is not an ideal fluid. Height of water in the final column was not equal to the initial values, which shows that there are friction losses in the water particles. This type of information is very useful in the case of nozzles, jets, and diffusers. And the conclusion from this experiment is that the experiment was to discuss the behavior of ideal and real fluid, and on the basis of the test results, it can be concluded that the experiment was successful because there is difference in measured and theoretical values. This is because of the friction losses in the real fluid. Ideal fluid does not have friction losses. From the experiment, it can be concluded that with the decrease in area of flow, there is an increase in velocity and increase in the flow pressure of the fluid. And that's all from me. Thank you.